Hello everyone, this is Chris again. I'm just continuing on along the lines of the fluid dynamics. This is part 2 in a series of videos on fluid dynamics as they relate more to the respiratory system and will kind of have more respiratory implications. But certainly fluid dynamics is a general concept, applies to many different things. So I left us off talking about different types of flow: laminar flow, turbulent flow, and transitional flow, the three major categories. And then I just kind of asked the question, well, how do we know? What tells us that there is laminar? What tells us there's turbulent? Is there a quantitative number, if you will, some quantitative value that can give us this information? And there actually is a quantitative value known as the Reynolds number. And so what I'm going to do is I'm just going to put the formula up for Reynolds number, and then it's more important that we talk about the concepts than the actual numbers that go into it, but certainly I'm going to talk about the units. So Reynolds number. Again, this is what we use to determine the presence of a certain type of flow. Really what this is going to do is tell us the difference between laminar and turbulent flow patterns. So the Reynolds number equals, and it's this little n there. Okay, so d mu p divided by n, what does all that mean? Well, d is the diameter of the pipe. Okay, diameter of the pipe. What do I mean diameter? What do I mean by diameter? If I look at a circle, if you remember from the pi video, from here to here, from the center to any point on the outer part of that circle is the radius, and 2 radii to r is the diameter. So the diameter is just a straight line through the center of the circle connecting 2 points on either end, or 2 times the radius. That's the diameter of the pipe or the tube or whatever we're talking about. This mu here, excuse me, is the average velocity of the fluid. And typically when we do our measurements, or when people do their measurements, these are all going to be in units of centimeters. Of course, velocity is a vector quantity. Put a little arrow above velocity, of course, so that they'll actually be centimeters per second of magnitude in a certain vector. This little p here is just the density. Density is mass per unit volume. So in this case, what we're looking at is grams per milliliter. Okay, so that's the top part here. The bottom part is the viscosity of the fluid. And the viscosity, how viscous something is, to give you at least a qualitative feel for something, how viscous. If you compare water to honey, honey kind of stretches, and there's a fair amount of intermolecular forces at play, and you can kind of stretch it, and it kind of slowly moves when under the influence of gravity. And it has this quality known as viscosity. Of course, honey is more viscous than water, and water is more viscous than air, and so on and so forth. So that's what viscosity is, and it's actually measured in grams per centimeter second. Okay, so these are the units. So basically what we do is we take the diameter of the pipe, the average velocity of the fluid, the density of the fluid, and we divide by the viscosity. So what Reynolds number is, in a very general way of looking at the Reynolds number, is I'm comparing the inertial forces, okay, the inertial forces. Remember inertia from Newton's laws. Inertia is a tendency for an object with mass to not want to move, or if it's already moving, then it doesn't really want to change what movement it has unless there's some sort of force acted upon it. more mass means that we have to act upon something with more force to get it to move. Well, that property of not wanting to move or not wanting to stop, that property is known as inertia. Well, that makes sense. You know, we have how dense something is, and density is nothing more than mass per unit mass per unit volume, grams per milliliter in this case, and velocity, right? Velocity is just nothing more than speed with a vector. In this case, you know, average velocity. Of course, instantaneous velocity would be the derivative of velocity, which would give us acceleration. But anyway, so we're talking about an average here. So these are the all inertial forces of that liquid, or that fluid, and I'm dividing those inertial forces by the viscous forces. Okay, we have viscosity here. However, let's look at our units. I have a centimeter here, centimeter second here, gram per milliliter here, and then down here, so this is my numerator, this is my denominator, I have grams, centimeter, second, and as you can tell, a lot of these things cancel out, and what's left behind is rubbish. It is just garbage. The unit that's left behind doesn't tell us anything. So what happens is the number that comes out of here, that falls out of this formula, is dimensionless. There is no real unit to describe it because we're using like units and like units, right? There's no comparison here. So it becomes just a number, just a dimensionless number. And I know that's probably pretty non-intuitive, but that's what it is. It's just a number. There are no units associated with that number. And from the number, from this comparison, comes kind of a generalization. And the generalization is, if my Reynolds number, okay, if my Reynolds number happens to be greater than 2,000, Reynolds number is greater than 2,000, that indicates that I have turbulent flow. If my Reynolds number is less than 2,000, that indicates that I have laminar flow. And, you know, obviously this isn't perfect, and, you know, you have a lot of transitional flow in between, but generally speaking, 2,000 is the number that we look at for the Reynolds number. So the take-home, and another take-home point that I just want to emphasize is that the numerator, so anything gets bigger in here, and my Reynolds number gets bigger, right? Numerator is directly related to what I'm looking at, x, if you want to make it that. The denominator, if this gets bigger, this gets smaller. So if I have a fluid that's very viscous, the more viscous something is, the lower Reynolds number will have, and that should make sense, that things like honey and corn syrup are very viscous, they don't flow very quickly, and of course they're going to be very laminar in the way they flow. And if I have things that aren't as viscous, they're going to be more turbulent in the way they flow. Likewise, the diameter of my pipe increases, or the velocity or the density increases, that is going to increase the Reynolds number. Now, of course, density is somewhat related to viscosity, or can be related to viscosity, but again, viscosity is more of intermolecular forces, okay? So, but there are some similar units in grams, but don't get those two guys mixed up. So, hopefully that makes a little more sense, and hopefully you guys have some intuition. I know it's very difficult to appreciate that I'm just using a number and there are no units with that number. It's a very crazy concept in my mind, but it's a concept that helps explain the difference, or it helps tell us, you know, what kind of flow pattern I have based on nothing more than comparing my inertial forces to my viscous forces. Okay guys, thanks again.